Today we will begin the second module of the course, which is regarding the minimum energy point and transistor sizing and circuit design for near threshold circuits. So, today we will discuss energy efficiency and minimum energy point. So, we will discuss minimum energy point, its origin, and what is its behavior with the changing activity factor of a circuit. This is important because several ICs, for example in a mobile phone, would have different activity factors in different operating scenarios, and then discuss a model for the minimum energy point with respect to activity factor, with respect to switching capacitances, with respect to the total size of the circuit and supply voltage, etc. And we will also discuss that for a given speed of the circuit, what is the minimum energy that you can achieve. So, that we will do next after we derive minimum energy point model, and we will discuss system level implications of this minimum energy point, how it would move, how it would change with architecture, with temperature, etc. So, we observe that when you simulate or when you measure for a circuit, you would find the energy per operation, or a certain operation, if it takes a certain number of cycles, you can say that in that operation energy per cycle, energy consumption per cycle. But what we really want is energy consumption per operation, and how that varies with change in supply voltage. So, in this course we are more interested in reducing the energy consumption per operation. The applications are such. So, you would want to do an operation and then the circuit remains in a standby mode for a long time. So, that is the reason. So, these are not continuously operating circuits. Usually they are in standby mode for a long time, and you want to reduce the battery life. So, you want to have the maximum possible number of operations done within the battery life. So, you want to maximize the total operations within a battery lifetime. That is one of the motivations. The other motivation is that you are generating energy, suppose locally you are generating energy. So, in that case, within that energy you want to do the maximum number of operations. So, you are not much concerned with power. So, power is energy per unit time. So, you are not trying to have maximum speeds. So, your main concern in these operations, in these kind of applications is that you want to do extend the battery life. So, and that is why energy consumption per operation is more important for us and not power consumption. So, what we find is that as you reduce the supply voltage, the energy consumption per operation, it reduces. So, the blue one, it is the dynamic energy, and the black one is the leakage energy. So, now leakage energy keeps on reducing in above threshold regime. So, that you can see because of the DIBL. So, as the reduces, because DIBL reduces, short channel effects. So, because of that, as you keep on reducing VDD, because in an inverter you would, if you have an inverter here, you would imagine that suppose the input is 0, then output is VDD. So, there is DIBL or short channel effects would then increase the leakage current of the inverter. So, therefore, with VDD it reduces leakage power. But there is also another effect which comes into being. As we go ahead, we will see that the leakage energy is not only dependent on leakage power, but it is also dependent on the time period. So, as we will discuss, so the time period would increase as you reduce the supply voltage. We will discuss this further, and therefore, the leakage energy increases beyond a point, and that is what we are observing here, that beyond this point the leakage energy is increasing per operation. So, dynamic energy keeps on reducing as you reduce VDD, because dynamic energy, as you know, is if we call it E dy in dynamic energy, it is, as we know, the gate input capacitance to VDD square. Now, if you multiply it with frequency, it becomes dynamic power. So, why gate input capacitance? Suppose you have a data path like this. So, the input capacitance of this is the load capacitance of this, and you would in a cycle, suppose this input falls and then again rises, then the output would initially rise and then fall. So, in the entire cycle, what you observe is that a charge q goes from VDD, it charges a charge q equal to Cg, suppose this is Cg, the gate capacitance, Cg into VDD, this charge charges the input of this when the input is rising, and when the input is falling, the same charge goes to ground. So, therefore, it is the energy is q into VDD, that the charge q moves from VDD to 0. So, in a simple way, we can say that over in a cycle, the energy consumption is Cg VDD square, dynamic energy consumption. So, that invariably keeps on reducing as you reduce VDD. What about leakage energy? That we will see in more detail. So, before we look into that, let us think of the time period, because we have passing in as a passing note we have discussed time period also. So, in this we have 3 stages, and suppose these 3 stages have delay of so this would have a delay of the random logic equal to T NAND plus the delay of NOR gate plus the delay of inverter. Now, we would like to express everything in terms of inverter delays. So, we will express this as some n times T inverter, let us call it n NAND plus some factor n NOR times T inverter plus T inverter. So, this is now the delay in terms of inverter delay. So, here you could have taken this to be common. So, we can write the total delay of the path as n NAND plus n NOR plus 1 into T inverter. So, this we call logic depth LDP. So, this is in terms of inverter delay. Now, one may ask a question, what is the load of the inverter? So, we can take it to be FO4 inverter delay. So, I would like to call it FO4 inverter delay. Now, let us discuss leakage energy. What do we mean by this? Now, in the logic path that we had seen, if we want to measure the leakage energy per cycle, now every gate would have a different value of leakage energy. Suppose you are looking at this NAND gate. So, when A and B are off or both 0, output is VDD. So, what is the leakage current then? The leakage current, so now this is 0 and here you have some leakage current flowing. For that to flow, the VDS of transistor B cannot be 0, it is greater than 0. So, there is a leakage current through this. Now, and the VGS of transistor A is now therefore lesser than 0. VGS of transistor B is equal to 0. So, it is, so therefore, the leakage current does not have a value of I off that we usually see. I off is the I current of a transistor for VGS equal to VDS equal to VDD. That is the definition of I off. So, it is not equal to I off. It depends on what is the logic gate topology. So, I leakage in this case is not equal to the defined I off as it is defined. So, I off is defined in the context of an inverter, because here when the input is 0 and output is VDD, you would find that the leakage current is I off. So, it would, and we can see another example. that suppose A and B are both VDD, then the leakage current is I of P MOSFET into 2. So, the leakage current, whatever its value, depends on the input values and the logic gate. So, when we want to estimate the leakage energy of a random logic, then we would need to know the logic gates in that random logic and also the input values. So, we would usually tend to do it over a long period of operation, so that all kinds of input values, all the input vectors, possible input vectors covered for the logic path, and you have an average leakage current of the gate. Now, the average leakage current would depend on the probability of inputs assuming certain values 0 and 1. So, we would have to consider this average leakage current for each logic gate. That said, now how do we estimate the leakage energy? Now, if we look at this timing diagram, now in the context of the logic circuit that we had discussed previously between a launch and a capture flip flops, different stages would switch at different times. So, this is for the NAND gate, the input of the NAND gate, then this is the input of the NOR gate, likewise, and this is the input of the third stage, suppose. So, you would observe that the NAND gate is operating is having just a leakage current, its switching is happening only here, it is having this leakage current for most of the part of the logic operation. Likewise, the NOR gate has leakage when its input is VDD and again leakage when its input is 0. So, it has a leakage current, its leakage current's value may change, but it has a leakage current for most of the part of the clock period, likewise for the third stage. So, for most of the part of the clock period, it is the leakage current which flows through the logic gate. Switching happens in a well designed circuit, the switching would happen only for an insignificant part of the logic of the total time period. Typically, in an above threshold circuit, we would observe that the logic depth has a value of 15 or so in a above threshold or super threshold voltage circuit, and in a near threshold voltage circuit, this would be some 7 or so typically. So, why would it be smaller in near threshold circuits? Because the speed or the delay of each logic gate is now quite large. So, that is why the logic depth is usually smaller. We will discuss this later. So, what is the switching period of one logic circuit typically, one logic gate typically? So, it would not even be 20% of the total clock period. So, that is why we assume that a logic gate would have the average leakage current passing through it for the entire clock period. So, therefore, the energy leakage energy is the time period of the clock into average leakage current of a leakage current of a logic gate. So, you add all the leakage currents for the entire logic path into VDD. So, this is the leakage energy. So, the inherent assumption here is that the switching time of each stage is negligible compared to the clock period. That is the basic assumption using which we derive this expression. Now, let us look at the time period. So, this is the time period. So, what is the value of this time period? Now, let us discuss the time period t. Now, we are operating in near threshold regime. So, suppose we are operating in super threshold regime, then what is the typical delay or delay of an inverter? Now, we are expressing all the delays of the entire logic path as we had discussed earlier in terms of inverter delay. So, now let us look at inverter delay. So, what would inverter delay be proportional to? So, this is an inverter, it is typically driving another logic gate which has a capacitance, equivalent capacitance given by C load. So, therefore, this inverter delay would be proportional to, or let us call it just CL, load capacitance. It would be proportional to CL into VDD, because this is the charge that must come to the load capacitance. This is the amount of charge, or which the amount of charge which must be discharged. Either it should be charged to this value from 0, or it is discharged from this value. And now what is the current? So, the delay should be inversely proportional to the current, because average current or switching current if you call. So, that current, now we are operating in a near threshold regime, that is you are quite close to the threshold voltage or slightly below the threshold voltage. So, what is the current that you would have? The current would again be in a super threshold voltage regime. The current would be proportional to, if we are assuming velocity saturation, the current would be proportional to typically VDD minus VTH minus VD sat for velocity saturation. And for pinch off related saturation, it would be proportional to VDD minus VTH square. So, we will discuss all that later. And in a leakage or in a near threshold or sub threshold regime, where the currents exponentially change with VGS, this would be proportional to exponential of VDD minus VTH minus some effect, secondary effect because of the drain induced barrier lowering or short channel effects. So, again it would come out to be lambda VDD divided by slope factor to VT. Now, this we will discuss all these current equations in detail later, more detail later. So, now you can see that in super threshold regime, the inverter delay increases or remains almost, so it increases, but increases quite slowly with a reduction in VDD, because the reduction in numerator and the denominator of this expression are quite comparable. So, in other words, the amount of charge to be, I mean the value to which the output capacitance needs to be charged or from which it needs to be discharged reduces, and similarly the current also reduces almost with the same factor or with a somewhat larger factor. If it is pinch off related saturation, then the reduction in current would be faster. So, but it would not be significantly faster. Whereas, in near threshold regime, we would observe that the inverter delay is now proportional to VDD into CL divided by an exponential relationship with 1 plus lambda VDD minus VTH by N VT, where this VT we are defining as KT by Q, thermal voltage. So, here we observe that as the value of VDD is reduced, the increase in inverter delay is much significant. Break. I is exponential. अच्छा अच्छा, that I have not, so proportionally इसलिए नहीं कर रहा था, है ना, इसलिए I not नहीं लिख रहा, proportional to कर रहा हूँ ना. Yeah, let us resume. So here as you reduce VDD, the denominator reduces, the denominator reduces exponentially, the numerator only linearly reduces. So, your leakage, your delay of an inverter keeps on increasing almost exponentially, or in other words, the discharge or charging reduces linearly, whereas the discharging current reduces exponentially. So, that is why the delay increases almost exponentially. So, what is the importance of this? That is why, as we had seen earlier, if we plot leakage energy with respect to VD, you would find that in the above threshold regime, this reduces because the delays increase, but the charging, the amount or the value to which the output node needs to be charged or discharged also reduce. And then as you go to lower voltages, the currents now start reducing exponentially with respect to the supply voltage. So, this a kind of flattens therefore. But then because the time period of the clock as we know is logic depth into inverter delay. So, as inverter delay increases significantly almost exponentially, the leakage energy which is proportional to the time period of the clock also increases almost exponentially. So, that is why we find this behavior, and this is so because of that, and the overall energy also increases as we had seen. So, the dynamic energy on a different scale would keep on reducing as a square law with respect to VD. So, the total energy would reduce with a minimum somewhere here and increase. So, I may not have, so we have a minimum for energy which is important. So, this we call minimum energy point, and that is important for near threshold or low voltage operation. You want to operate somewhere near the minimum energy point. You may not be able to operate exactly at that value of VDD, but you would like to operate closer to the minimum energy point, so that your energy efficiency is maximized. So, typically one would have a doubt why we are not discussing short circuit energy. In low voltage operation or in near threshold operation, suppose let us take again the example of an inverter. In super threshold voltage operation or nominal voltage operation, you would find that if you have an input, the output would input of this kind, rising input, the output would behave usually in a well designed circuit. A significant discharge of the output would happen within the time duration when the input is rising. Whereas, in near threshold voltage operation, because the currents are increasing exponentially, the currents increase exponentially with V in. So, you would find that maximum discharge of the output would take place when V in is close to VD. That is where you have maximum current. The difference in current for a little change in input voltage would be quite significant, because it is an exponential increase in the current with V in. So, therefore, most of the discharge happens when the input is close to VDD. So, in the near threshold voltage regime, you would find that if this is the input, the output would behave almost like this. So, most of the discharge is taking place in a well designed circuit after the input has almost risen to VDD, or after the input has come very close to VDD. So, in super threshold voltage regime, you would find that there is a window when both PMOS and NMOS are on, both are on, both are not off. So, therefore, in this window there is a short circuit current from VDD to 0. So, that leads to a short circuit energy consumption. Whereas, here in near threshold voltage regime, when the P MOSFET is on, the N MOSFET is on. So, in near threshold or subthreshold voltage regime, you would not say on or off, but you would say that P MOSFET is conducting, N MOSFET is not conducting. So, what we want to say is that the P MOSFET and N MOSFET are not simultaneously conducting. So, short circuit energy can be neglected in near threshold regime. Therefore, we did not discuss it while discussing minimum energy point. So, in summary, what we would say is that short circuit energy we are not considering, and dynamic energy reduces as a square law with VDD, time period increases exponentially with VDD reduction in near threshold regime or subthreshold regimes, and leakage energy per cycle or per operation therefore increases exponentially as the supply voltage is reduced, and minimum energy point therefore exists for every circuit, but now it is circuit dependent. What is the logic path? Because as we had seen, the average leakage energy is a function of the logic gate topology and also what are the values that inputs issue. So, therefore, this minimum energy point can be different for every circuit, but nevertheless it exists for every circuit. Thank you. We will discuss further on minimum energy point in the coming lectures.